Hi, everybody. Welcome back to week 2 of the Enrico Fermi Institute Compton lecture series. This is Neutrinos, Detectors, and Discoveries. And today we're going to be talking about a new topic, so continuing our story of neutrino discovery with a couple new detectors along the way. Okay, so just a quick review. In lecture 1, we covered a couple things. So we covered how the neutrino was discovered and what its properties are. And then the key points here are that the neutrino is electrically neutral and it only interacts very weakly. So in order to see it, you either need a lot of neutrinos or a really big detector. We also looked at 2 very important experiments in the history of neutrino physics. So Reines and Cohen detecting the neutrino for the first time at a nuclear reactor using a double coincidence technique, where the neutrino produces a prompt positron and also a neutron. And the coincidence of those 2 signals allows you to see neutrinos. And then the other experiment was by Letterman et al. They used a spark chamber to show that the muon neutrino was different than the electron neutrino. And we'll revisit both of these in the context of looking at other neutrino sources today. So this lecture is titled Neutrinos from the Sun and Sky, and it's all about exploring natural sources of neutrinos. So the story starts with chemical reactions. So if a neutrino, as we saw in the last lecture, can change a proton into a neutron, then it should be able to induce certain chemical reactions. And in particular, this one, this 37 chlorine plus a neutrino makes 37 argon plus an electron. This was identified back in the 40s and 50s as a good candidate for one way you could detect neutrinos. So the idea here is that you make a big tank of chlorine. You wait for a little bit for neutrinos to interact with that chlorine and flip some of those chlorines into argon, and then you count the argon. And this has just nice chemical properties that made it a useful reaction to study. So the 2 people to propose this were Bruno Pontecorvo, Luis Alvarez. They both proposed the method, but they never did the experiment themselves. It came down to this scientist here, Ray Davis, who is a chemist by trade, to actually implement this into an experiment. So just like Reines and Cohen, Davis put a big tank of chlorine at a nuclear reactor to study neutrinos, to see if you could see any neutrinos from this reactor. And the reason for this is just that nuclear reactors have a lot of neutrinos. It gives you the best chance of seeing something. But what he saw was nothing. So this is a paper Davis published. You can see in the title, it already kind of gives it away: attempt to discover or to detect antineutrinos from nuclear reactors. So there were actually no events observed in Davis experiment that looked like neutrinos. And to understand why this didn't work for Davis, but it did work for Reines and Cohen, we have to go a little bit back to concept of particles and antiparticles. So what is an antiparticle? So a particle and an antiparticle, they're related by the fact that they have the opposite electric charge. But they have the same mass and they experience all the same forces. So for one common type of particle, the electron, it has a charge of -1 and a mass given by the mass of the electron, which we can measure. There's also the anti-electron, also known as a positron. So it has a charge of +1 and a mass of the same mass as the electron. So then the question becomes, well, what's an antineutrino? Well, so antineutrinos, as we know, are electrically neutral, so they don't have this opposite charge. So we can't actually put a plus or minus by a neutrino. Instead, what we have to do is indicate it's an antineutrino by putting a little bar over it. So we call these electron neutrinos and these electron antineutrinos or anti-electron neutrinos, something like this. But what differentiates them? And this is a very deep topic in physics that we'll come back to in future lectures in other contexts. But for now, the key idea that we'll need for this lecture is to study something called lepton number. So what is lepton number? It's just another type of charge. You can think about it as electric charge, but instead of having some interaction with the electromagnetic field, lepton number is something that is preserved in particle interactions. And so we can assign a +1 to everything that's a regular particle and a -1 to everything that's an antiparticle. So for electron neutrinos, those are regular matter particles. They have a +1 number, but anti-electron neutrinos are down here. We'll call their lepton number -1. So let's get a little practice with this. So playing by the rules. So we can look at a process like this. This is a muon neutrino plus a proton to a mu minus plus a neutron. So the question is this allowed? And we can see whether or not it's allowed by counting up all these different charges, all these different numbers. So on the left side here, Actually, yeah, let's see. So on the left side here, so first of all, this is not allowed. On the left side here, we can count up how many muon numbers we have. We have one muon neutrino, and we have one muon, so that actually checks out. They're both the same between here. But the proton has +1 charge, and on the right side, we have a minus charge and a neutron here. So this is a net of -1 charge. So this is actually not allowed. We can fix this interaction by doing a little swap. So if we replace the proton for the neutron, now we have the correct lepton number as before, but on this side we have the neutrino, which is neutral, the neutron, which is neutral, so 0 charge, and then on the right side we have the muon, which is negative, and the proton, which is positive, so again, net 0 charge. So these are the basic rules that determine whether or not certain particle interactions are allowed. We can also ask for other processes. So this process includes an antineutrino. So again, the antineutrino has a lepton number of -1, and the positron also has a lepton number of -1. So this looks good so far. Let's check the charge. So the proton has a positive charge, and the neutron has 0 charge. So it looks like the left side and the right side agree on electric charge as well. And yeah, that's the case. So this process could be observed. How about this one? This is muon decay. So a muon can decay into an electron and then also 2 neutrinos. So again, we can play the same game, just check to see which numbers are conserved. And I won't walk through it all, but yeah, on the left side, you have the muon number as before. There's no electron number on this side, and then charge is minus over here. On the right side, by counting up the neutrinos, we can count up the muon on the electron charge. But we've actually made a little bit of a mistake here, which is that we've put an electron and an electron neutrino on the same side of the equation. So this is actually not allowed, but we can fix it, again, just by making one correction, which is to switch this neutrino into an antineutrino. Now the lepton number of the antineutrino cancels with the lepton number of the electron, and you get 0 on both sides. So this is the way to see which interactions work or not. There's one other thing, which is that you can't forget about energy. So I've talked about charges, but also these things, all these particles have mass and energy, and those things also have to be balanced. So this is the same, one of the same reactions I showed from the previous page, but now let's talk about what energy the particles need to have for this to happen. So in a typical particle detector, you have a big mass of something that you're watching, so all that mass is at rest. So for example, like the neutron, which might be in your detector, would be at rest. So it's really up to the neutrino to have enough energy to make this reaction go. So you can calculate the minimum energy required for this reaction by assuming that the muon that comes out on the other side is at rest. And if you do that, the equation looks like this, and you can plug in these masses down here to find that the muon needs about 110 MeV of energy for this reaction to happen. So energy is also very important to keep in mind. This reaction couldn't happen if, for example, the muon neutrino had less than 110 MeV of energy. So just one example of this, the tau particle was discovered in the 70s. This happened at Stanford Linear Accelerator, and they found it by smashing electrons together and seeing what comes out. So the tau is a lepton just like the muon and the electron, but it's even heavier than the muon. So for scale, something like this, the electron is very light, the muon is heavier, and then the tau even heavier still. So if you wanted to produce a tau and a neutrino interaction, you can do the same kind of formula as we showed on the previous page. So plugging in the mass of the tau, which is 1,700 MeV, you find that the minimum energy for the neutrino has to be about 3,400 MeV, just using this formula. So you need a lot of energy for that neutrino to produce the tau particle. Okay, so back to Davis's experiment. So why didn't Davis see anything? So we can look at the kind of reactions involved in this experiment. So remember, the nuclear reactor was producing neutrinos from beta decay. So you have a neutron, and it decays to a proton, an electron, and an electron neutrino. And then what Ryan and Cohen were looking for was that electron neutrino interacting with a proton and producing this double coincidence signature, so the positron and the neutron. Davis, on the other hand, was looking at this chlorine-argon reaction, a chemical reaction. So Davis wanted to see the electron neutrino plus a proton go into a neutron and an electron. Slightly different, mostly in the signs here. So we can understand this is happening because, based on our rules, the electron that came out of the beta decay must have been an antineutrino. So in other words, this neutron can't go to a proton plus an electron plus a regular neutrino. It has to be an antineutrino to preserve this lepton number for this reaction to happen. And then if you plug that antineutrino into what Reines-Cohen we're looking at, now this equation balances. You have this -1 electron number on this side and a corresponding -1 electron number on this side. For Davis, this reaction can't happen because it's -1 electron number, and the electron that would be produced would have a +1 lepton number, so it's not balanced. And that's why Davis didn't see anything in his experiment, because the neutrinos he was looking at were the wrong sign. They were antineutrinos, not regular neutrinos. Okay, so then what about the sun? I mentioned this at the beginning or at the end of the last lecture. This physicist over here, John Bacall, had one burning question his entire life, which is, do we understand how the sun shines? And he identified correctly that the sun should produce a lot of neutrinos, and we could use those neutrinos to say something about what the sun is doing, how its processes, or what processes drive it. So the basic idea here is that you have fusion in the sun, and you have two protons. They form a deuterium, so there's a proton and a neutron in a bound state, and they emit a positron and a neutrino. And the positron that's emitted here, to balance the right side of the equation, needs to be associated with a regular neutrino. So this is exactly what Davis needs. But first I'll give you a little bit background about the sun. So how does the sun work? So the sun has different regions. In the core, this is about 20% of the sun's radius, very hot, 27 million degrees Fahrenheit, and it's also very dense. These are the conditions that we're trying to recreate on Earth to do fusion reactions, and it's very difficult, as you can imagine. But it happens in the sun for free, and we benefit from that because it produces a lot of energy. So this process that Bacall identified as two protons fusing together, that's happening all the time in the middle of the sun, and it's producing deuterium and a lot of energy. But this process doesn't stop here. So once you have the deuterium can then fuse with other protons and produce even heavier elements. And each time that happens, you get an energy release. You get a lot of radiation, so light that we see. That light takes a long time to make its way out of the core. So specifically, the light is interacting and re-interacting and bouncing around in the inside. It's very dense inside the sun, so the photons interact a lot as they stream towards Earth. The neutrinos, on the other hand, that are produced, they come basically straight from the core, so where the fusion is happening, and they're not impeded by the matter in the sun. So they just stream out. Okay, so solar neutrinos are produced from fusion, and we think about this in terms of a chain of events. So the first part of the chain is hydrogen fusing into deuterium. So these H's are the same protons we were seeing before. When they fuse together, you get this positron plus the neutrino. We call this the proton-proton chain, neutrinos from the proton-proton chain. That deuterium then fuses with another proton, making helium and a photon. Going on even further, you can add helium together with other isotopes of helium to produce even heavier elements. So in particular, there's this helium proton chain that also produces a neutrino. You can also start to form other elements like beryllium here. That beryllium then can fuse with other things, or it can decay. So there are two branches here of this path. So the beryllium plus the electron makes lithium and a neutrino. We call these beryllium-7 neutrinos. And then over here, beryllium plus proton makes a boron-8, which then decays into an electron neutrino. So we call these boron-8 neutrinos. And we can look at all of these neutrinos in a spectrum. So this is something that John Bacall had worked on, and it's basically plotting the intensity of neutrinos on the vertical axis against the neutrino energy. And all of these different things are different neutrinos from different processes in the sun. And this is the prediction of how many neutrinos you should see and at what energies they should have. So I'll just walk through this a little bit. So the first thing to notice is this vertical axis, which goes up to 10 to 11. So literally what this is saying is that there are about 100 billion neutrinos passing through every square centimeter of Earth per second. So just an enormous number of neutrinos from the sun. But these are all super low energy. They don't interact very often. And that means that you're not in danger of being affected by neutrino radiation. But the number is very important. Okay, so then there are these different lines here. So the first one here is boron-8 that I'm going to highlight here. And boron-8 is kind of special because its energies go out to the highest, almost to the highest on this plot. And the flux of boron-8 neutrinos is pretty high, so there are a decent number of these. The boron-8 neutrinos are similar to other lines on this plot in that they come out of three body decays. So what I mean by that is that when the fusion happens, there are 3 different particles that are produced from the fusion. And just like in beta decay, when there are 3 particles at the other end of your reaction, you get a broad distribution of energy. So momentum can be conserved by splitting that energy between 3 different particles. So that's true of this boron-8, also of this HEP over here. And then you can contrast that with, instead, like beryllium-7, this fusion process only involves 2 particles. So when the particles fuse, 2 particles come out. Momentum has to be conserved between them, so the energies of these neutrinos are totally fixed by conservation of momentum. So that's why they form these vertical lines here. Okay, there's also fusion from even heavier elements than the one I showed on the previous page. This is called the CNO cycle, the carbon, nitrogen, oxygen cycle, and that also can produce some neutrinos. The fluxes here, they're a little bit less, or there are fewer of them than the proton-proton neutrinos up here, and their energies are kind of in between the boron-8 and the proton-proton neutrinos. And these will come up a little bit later. Okay, so detecting solar neutrinos. So in the last lecture, we talked about 2 types of detectors we could use to detect neutrinos. So first, Reines and Cohen looked at this double coincidence. Letterman et al. Looked at the spark chamber to use them. Unfortunately, we can't use either of these to detect solar neutrinos. So first of all, the inverse beta decay reaction, as I showed on the previous couple of pages, that requires antineutrinos. And all the neutrinos coming from the sun are going to be regular electron neutrinos. There's also the spark chamber by Letterman et al. That was used to tell apart the electron neutrino from the muon neutrino. Unfortunately, this requires that the neutrino has a lot of energy, and the energies of the solar neutrinos are usually about under 10 MeV or so, whereas Letterman et al. Were looking at neutrinos with hundreds or even 1,000 MeV of energy. So this also won't work. They're too low energy to be seen in the spark chamber. But fortunately, we have Davis. So Davis's chlorine reaction is what we're going to use to try to see these solar neutrinos. So the reaction threshold for this process to happen, I talked about how much energy you need for it to happen. Luckily, chlorine switching to argon through a neutrino, that takes about 0.8 MeV. So Davis should be able to see all the neutrinos starting from here and on in some combination or another. Okay, so, but actually Davis already did this in his first paper. So the same paper we saw before, at the end of the paper, Davis has a comment saying like, well, I didn't see anything from a reactor, but I should see something from the sun. And what he does is he sets a limit. So he didn't see anything in that experiment, but he set a limit based on how big his tank was and how many neutrinos he expected from the sun. And he didn't see anything. So why didn't Davis see anything yet again? Well, there was an interesting comment left on his article. So any experiment such as this, which does not have the requisite sensitivity, really has no bearing on the question of the existence of neutrinos. And then this reviewer of Davis's paper goes on to say, to illustrate my point, one would not write a scientific paper describing an experiment in which an experimenter stood on a mountain and reached for the moon and concluded that the moon was more than 8 feet from the top of a mountain. So kind of a brutal review, honestly, and a little bit unfair, I think, because nobody else had done this before. Nobody else had looked. So Davis looked for neutrinos, didn't find anything, said, okay, well, here's my conclusion. And then the reviewer said, well, you weren't going to see anything anyway. But okay, so why did the reviewer think this? The problem is basically that neutrinos aren't the only way to produce the argon-37 that Davis was looking for in his experiment. So charged particles that are produced in the atmosphere can also do it. And Davis's experiment was essentially this. He had a big tank of chlorine, and every once in a while he would expect a neutrino from the sun to interact and flip one of the atoms of chlorine into argon. But most of the time, what he was seeing was just cosmic rays from the atmosphere, entering his detector, flipping chlorine into argon. And so most of the argon in his experiment was actually due to these. So Davis's experiment was essentially looking for a couple extra argon-37 atoms on top of a big background of maybe 100 or 1,000 every time he counted them. So very impossible search to conduct. So the solution to this is to actually get rid of these cosmic rays. So in this paper by Davis in '64, Davis talks about the advantages of moving your detector underground. So Davis realized that you can get rid of these cosmic rays by burying your detector far deep in the Earth. And so he calculates the number of cosmic particles that could induce this reaction as a function of the depth of your detector. And so at 25 feet below the surface, you get about 6,500 of these background particles. However, if you start moving your detector deeper and deeper, you can really get this number down by a lot, so almost to 0 expected background counts. The only problem is that now you have to put your detector 4,000 feet underground, which is not an easy task. However, if you can do it, then every argon atom that you count in your detector, you could attribute to a solar neutrino. So that's the basic idea. It makes your measurement a lot easier. So that brings me to the homestick experiment. This is in Leeds, South Dakota. This is a little picture of the town from a postcard. It's a mining town, and up here you can see this is the mine shaft, and that mine shaft goes to a gold mine. And Davis found or made some agreement with the gold mine to let them put his detector down underground. So specifically, this mine shaft will take you on an elevator all the way down 4,850 feet, and this is where Davis put his experiment in this gold mine. So it was a great idea, and this is the detector built in the gold mine. Here's what it looks like. This is the chlorine tank over here. There's a walkway that goes on top of it. There are lots of pumps for purging the chlorine and counting the argon. And then here's the way out. So you have to be able to get out once you get down. So this is the way back to the elevator. Okay, so here's what it looked like. This is an actual photo of it. This is Davis on top of his chlorine tank in the mine. So you can see this is the walkway, and then this is the mine with all the reinforcements up. So Davis actually did this experiment, and what he saw was nothing, unfortunately. So kind of a bummer. This is a note he had from proceedings in 1970 after running his experiment for a little bit. So he looked at the production rate of argon and found that it was totally consistent with 0. So that's kind of a bummer, but Davis didn't give up. So this was just at first. So you can have statistical fluctuations, things can go up and down. And actually Davis ran this experiment for about 25 years. And this is Davis's data across that whole 25-year range. And certain months of the year, it was 0, so you can see down here. But other months, it wasn't. And what you can do to make your measurement more robust is to average everything together. And at the end of these 25 years, what Davis found was that you had a very precise non-zero measurement of the argon-37 rate. So this is great. So Davis is actually seeing some excess of argon-37 that he can attribute to solar neutrinos by having this detector underground. The problem is that the solar neutrino predictions are all the way up here. So Davis measured something like 1/3 of what was predicted by all the solar models, three times higher. This was a really big issue and it became known as the solar neutrino problem. So basically, John Bacall, who had predicted the expected rate of solar neutrinos, and Davis's experiment, they didn't agree with each other. So what's the deal? Actually, this was not solved for a long time. There was another group of experiments that tried to use a different chemical reaction to do this. And the one they picked was gallium to germanium. And the reason why this was chosen was because it has an even lower threshold than Davis's experiment. So here are two examples of experiments that were run in this configuration. And they had results that were released in the 90s. They also found a deficit of solar neutrinos compared to the prediction. But they were actually studying the neutrinos from a totally different source than Davis. They were mostly seeing these proton-proton neutrinos appear, whereas Davis was mainly seeing these boron-8 neutrinos. So this was a really nice cross-check, that this was not just a problem with the boron-8 neutrinos, this was a problem with all the neutrinos in the sun. Okay, but at this point I need to take a slight sidestep, because the story of solar neutrinos is not complete without the story of proton decay. So what do I mean by proton decay? So not everybody was interested in neutrinos back in the 70s when Davies was doing this. Another very exciting part of physics was to look for a process that involves a proton becoming an electron plus another particle, in this case the pi zero. So if you ever saw this process happen, it would indicate that there's some new type of physics happening, some new force. And the reason why you can see that is because the proton is not composed of any leptons, but there's a lepton on this side of the equation. So this violates one of our rules from before. But if you can see this process, then that's evidence that that rule is broken and there's some extra force in the universe that we don't know about. So the way these experiments would work is that you would have a detector containing lots of protons. Those protons would be mostly at rest, and then you would look for a signal of an electron or a positron in this case of just appearing in your detector with a very specific energy. So once again, the proton's at rest. The positron would be emitted with a fixed energy in this two particle decay. So you would look for this kind of electron that happens. And this is much higher than a solar neutrino, but just bear with me. I promise we'll get back to those in a little bit. To do these experiments, you need a lot of protons. So remember Reines-Cohen, they used 100 liters of water in their experiments, and that was about 10 to the 27 protons. So can we do even better than that? And it turns out we can. So this is an example of the IMB experiment. This was in, IMB stands for Irvine, Michigan, Brookhaven. These were the three institutions that came together to build this detector. This was on the, I think on the edge of Lake Erie in Ohio. It contained 2.5 million gallons of water, and it's about 10 to the 31 protons. On the edge of the IMB detector, what you have are these photomultiplier tubes, and there were about 2,000 of them. And then this is my prop, actually, for this week. This is what the photomultiplier tube from IMB looked like. So they were 8 inches about, and this would be mounted to the wall of the detector. And then any light that happened inside your tank would be detected by this thing. So that's how it basically worked. Yeah, so I told my advisor for my PhD that I was giving this lecture series, and he said, "Great, do you want this PMT?" And I said, "Well, not really, like it kind of takes up a lot of space." And he was like, "No, you should really have it." I think he was doing some spring cleaning, but anyway, it's here. This is the IMB experiment. This is where this PMT came from. Okay, there's another version of this, which is Kamiokande. This was built in Japan. So this stands for Kamioka Nucleon Decay Experiment. Kamioka is the town that this is nearby. 1 million gallons of water, so also roughly 10 to the 31 protons, but a factor of 2 less than IMB. So the proton decay limit or proton decay search that they could do was not quite as precise. But they did have one advantage, which is that they had a much denser coverage of phototubes. So this is an example of the Kamiokande model. So this is a 20-inch instead of an 8-inch, so much bigger than this one. And the detector was really covered with these things so that you can see, I'll just flip back to IMB for a little bit, there's a lot of space between these, which is fine if you're looking for something very energetic, but if you want to see something low energy and collect a lot of light, collect every possible light possible, then you want to really instrument your detector with a very dense array of these photomultiplier tubes. Okay, so, and then of course this thing was also filled with water. So here's a picture of that, filling this whole detector with water. Okay, so then I want to mention just a little bit about how it works. So the basic principle for both of these experiments is shrink-off radiation. So you start with water. Water has an index of refraction of about 1.33. If you have a particle that's moving close to the speed of light, then what happens is that the radiation emitted by that particle will be traveling slower than the particle itself. And that means that the radiation that's coming out off of the particle will start to form these wave fronts that lag behind the particle. And the amount of lag is proportional to the index of refraction of the medium that they're traveling in. You can do some geometry and calculate the angle of this radiation, how it's emitted. And what you find is that it's given by the inverse cosine of 1 over the index of refraction. So plugging in some numbers for water, you find that this angle is about 42 degrees in water. And this has a nice property, which is that if you follow this radiation towards the walls of your detector, it actually makes rings when you look at it in 3 dimensions. So you take these lines of the radiation that the particle is emitted. If you follow them to your walls where you have your photodetectors, what you would actually see when looking head-on to the particle would be a ring of light. And that ring of light tells you a lot of information. It tells you where the particle came from and how much energy it had, for example, by how much light is in the ring. So we're finally back to solar neutrinos. There were these proton decay experiments, but they realized while they were waiting for proton decay, which takes a long time, we actually have never observed it yet, it was realized you could do something else with your detector. So boron-8 neutrinos in particular from the sun had enough energy to produce electrons that were energetic enough to make rings in these detectors. The only problem was that these detectors weren't designed to do this, so they had to be upgraded. So in particular, the Kamiokande experiment was upgraded with a new water purification system to be able to see lower energy particles than what they were looking for. And they had installed a cosmic ray detector so that every time there was a cosmic ray, they could throw out the event. They could only look at events that were clearly not cosmic rays. And here's the basic geometry of the problem. The sun is producing these neutrinos. As they come into the detector, they interact and they scatter off and they produce this electron, which then produces the ring on the side of the cylindrical tank. So here's what an actual event looked like in Kamiokande. This is Kamiokande data from published in 1992. This is a geometry of their detector, and then here's this ring that they fit from their data. If you unroll the detector, so you separate the 2 caps and then unwrap the sides of the detector, this is the view where you can clearly see that there's a ring pattern formed here. The size of these dots is showing how much light was detected by each PMT. So this is actual data from Kamiokande. And what this allows you to do that Davis couldn't do is make what we call a real-time measurement. So what this plot is showing is every electron that was observed that is consistent with a solar neutrino and the angle with respect to the sun. So back to this diagram here, the sun is producing a neutrino, which then produces an electron in your detector. You can ask what is the angle of that electron relative to the sun at the time you detected it. And what you find when you add up all the counts in this way is that you get this distribution that has a peak in the direction of the sun. So you can be sure that these neutrinos are actually coming from the sun. They're not just noise. So this confirmed that, and then the other thing, so then you can break this distribution down into 2 parts. There's a flat background here. So the experiment was not totally background free, but above the background, there's this excess region here coming from solar neutrinos. Davis was not able to do this. Davis's detector has no direction information. All Davis could say was whether or not there were more or less argon-37. But this measurement by Kamiokande really confirmed that what Davis was seeing was electron neutrinos because they also measured a deficit. This solid line here is the prediction of the neutrinos, and the Kamiokande experiment was still missing them even when they could see them in this real time as a better cross-check. So I'm going to show something else you can do with this idea. So this photo here is a picture of the sun taken from one of these Water-Shrenkov detectors. And on top of it, I've overlaid this plot from this previous page. So what are we seeing? This is a picture of the sun, quote unquote, in neutrinos, but really what we mean by that is that each pixel of this image is the intensity of electrons versus their relative angle to the sun. So it's kind of like a camera, but it just takes a long time to build up the image. And so what you can see is that the sun's direction can be inferred from this plot as the bin here where the counts are at their maximum. So really this is not showing necessarily that the sun is immersed in a cloud of neutrinos. What it's showing is that the electrons produced from the sun are very blurry. They don't always point back exactly to the sun, but they mostly do on average. So the sun in this image is just like this very central pixel here. And then the rest are electrons that have been scattered by the sun, but you don't totally get their direction pointing back directly at the sun. So it's a very blurry image of the sun made with neutrinos. So kind of cool. Okay, but for now, I just want to table the discussion of solar neutrinos because what feeds into the rest of this talk is also from the sky. So I mentioned last time that you can use a neutrino beam. You can make a neutrino beam by accelerating protons that hit a block of material that will produce a spray of pions. Those pions decay into neutrinos. It turns out that the same process is happening all the time around the Earth. But instead of this block of material and a proton from a particle accelerator, you have a cosmic ray, and that proton is hitting something in the atmosphere, like an oxygen or a nitrogen or something like that. So this process is happening all the time, and this process is what we call atmospheric neutrinos. So same diagram as before. You have a proton, it interacts with some nucleus in the atmosphere, produces a spray of pions. Those pions then decay, just like they did in the neutrino beam experiment by Letterman et al. The Earth acts as a shield against these muons. So the muons, they might travel a little bit into the Earth, but then they get stopped by the matter. The neutrinos that are produced in these decays pass through. The reason Davis moved underground is the same reason here. So these muons that were produced from these pion decays in the atmosphere are being blocked by the Earth. So the deeper you go, the fewer of these muons you have to deal with. Okay. The other thing that can happen is that the pions can decay before they reach the Earth. In that case, they produce muons, which can then also decay. The muons that are produced by the pions can decay before they reach the Earth, also producing neutrinos. And so what you get is neutrinos of all different flavors here. So there's a muon neutrino, anti-muon neutrinos, electron neutrinos, anti-electron neutrinos. They can all be produced through this process. Okay, going back to Kamiokande for a little bit, here's what those atmospheric neutrinos look like in the Kamiokande experiment. I have two event displays here. The left one is showing a lot of charge in a big ring, so shrink off like before. The other one showing a little bit less charge and a little bit fuzzier. And actually, how to understand this process is the same way that we looked at last time. So a muon doesn't scatter very much. When it enters a detector, it's very heavy. And this is what Letterman et al. Used to separate muons from electrons, the same concept. So remember in the spark chamber from last time, the muon traveled in mostly a straight line, and that's exactly what's happening here. The muon is traveling in mostly a straight line, so it doesn't scatter very much. On the other hand, electrons do scatter because they're very light, and what that means is that as the electrons travel through your detector, they kind of spread out a little bit, and they make what we call fuzzy rings. So you can tell the difference between a muon and an electron in a shrink-off detector by looking at how sharp or fuzzy the ring is. Okay, so back to this diagram of atmospheric neutrinos. What's the actual thing we're measuring here? So you can imagine you have a detector on the surface. This is Kamiokande, and you have atmospheric neutrinos coming at it from all directions. So you have atmospheric neutrinos that are produced in the sky directly above the detector, some that are produced close to the horizon, and some that are produced on the other side of the Earth. So what you can do is you can look at the direction of the neutrinos entering your detector and ask how far did that neutrino travel. So if your neutrino is pointed straight down, then you can infer that it was produced in the sky directly above you, and that means that the average distance from the neutrino's production point to your detector is about 15 kilometers. So on the other hand, if your neutrino is coming up from below your detector, then you can infer that that neutrino traveled across the entire Earth before it reached your detector, and that is a distance of about 13,000 kilometers. There's a little bit of geometry, again, here that you can do with this. So one common way to write this is cosine of the zenith angle, where the angle is just telling you what the direction of the neutrino was with respect to your detector. So I'm going to show some plots on the next few slides that use this variable. The interpretation of it is that if your cosine zenith is near 1, then your neutrino is downward going. So this is neutrinos with very short paths. On the other hand, if your cosine zenith is -1, then that's a neutrino that was produced on the other side of the Earth. So when it enters your detector, the ring is going upward, is pointed upward. Okay, so here's what Kamiokande looked at when they, or saw when they looked at neutrinos from the sky. So instead of the sun, this is now the sky. On the left, these are the so-called fuzzy rings. These are the electron-like events. And then on the right, these are the sharp rings, so the ones that look like muons. One other thing I'll point out is that these are labeled as multi-GeV. That means they have about 100 times as much energy than the solar neutrinos. So these are a different type of neutrino, and the solar neutrinos don't enter here as a background in this particular way of looking at the data. But what they started to notice is that, so I'll just annotate this a little bit. What they started to notice is that there was kind of a deficit of neutrinos coming down here. So what's going on here is that cosine zenith of 1 over here, these are the downward going neutrinos. This is about 15 kilometers of travel distance. These upward going ones, this is about thousands of kilometers of travel distance. And there's this kind of weird shape to the data. It's supposed to look like this kind of stair-step pattern over here, but there's kind of a deficit down here. And this was just one of several different hints at the time. So if you looked at other experiments, so back to IMB, they also did this measurement. They looked at these energetic muon events in their detector, and they also found that compared with the expectation of how many neutrinos they should expect, they were seeing fewer in the downward going direction. Here's another experiment, macro. I didn't talk about this one, but same idea. They're looking at neutrinos. They see that neutrinos are kind of missing at these most upward going angles. So the neutrinos that travel the furthest tend to be a little bit missing. Okay, so I'm now going to try to bring these different things together. We have the solar neutrinos where Davis and Kamiokande were missing events, and then we have the atmospheric neutrinos where all these experiments were seeing something that was missing at longer baselines. So the not so simple idea is that what if neutrino flavor changes over time? And I plan to get back to this at the next lecture. But for now, we have to change our mental model of a neutrino just a little bit. So instead of picturing a neutrino as a fixed 100% electron flavor, what if it's more like a pie chart? What if one neutrino could have multiple flavors in it? And this is not just kind of a random idea. There was many decades of theoretical work leading up to it that kind of started back in the 50s with Bruno Pontecorvo, the same Bruno who proposed this chemical reaction that Davis used to see solar neutrinos for the first time. And then following with the theoretical framework all the way to an application of solar neutrinos around the 80s. One of the members of this theoretical work was Lincoln Wolfenstein, who was a PhD student here. Okay, so what does this new model of neutrino give us? So before, what we were looking at is assuming that an electron neutrino appears at our detector at Earth, and there are different processes that electron neutrino can undergo. So in one case, the electron neutrino can do this. It can interact with a neutron and just scatter off that neutron. Nothing exciting happens, so nothing changes into an electron, and the neutrino just flies out of the interaction, but it might give some momentum to the neutron. So in this case, this X, I'm calling this new X, can actually be anything. It could be an electron, it could be a muon, it could be a tau. You can put in whatever neutrino you want into this process. But anyway, the electron neutrino will do this process too. On the other hand, it can also do this process where it does interact with a neutron, but it changes that neutron into a proton, and outgoing from that reaction is an electron as well. So this is the solar neutrino kind of model. So both of these processes happen, but now if we substitute in our new model of the neutrino, what happens instead? So again, the neutrino, we can now think of it as a pie chart. This reaction here is unaffected, so this first one, because remember, the neutrino could be anything. So it doesn't matter what the type of neutrino it was when it came into the experiment. This process will still happen. This process will still happen. On the other hand, this other process is going to be reduced a little bit. And the reason is that because this process relies on electron neutrinos entirely. If the neutrino is now a mixture, then this process will be reduced by the factor of the mixture that it is. So this process is reduced. And then other processes should also happen to take its place. So instead of having the electron, you have some muon component, some tau component, and then this process should happen where the muon or tau neutrino changes a neutron into a proton and then also produces the corresponding muon or tau particle. But in the case of solar neutrinos, there's not enough energy to do this, just like we saw at the beginning. You need to have enough energy to produce those heavy particles for this reaction to happen. And for solar neutrinos, which are about tens of MeV, this is forbidden. So in your experiment, what you would expect to see is this process is unaffected, but this process would be reduced because some of your neutrino is not electron type. We can also look at the atmosphere. And so the idea here is that the neutrino is a mixture, and that mixture changes over time. So going back to the atmosphere, if you start with a muon neutrino, and you can imagine that as it travels, it gains a little bit of electron and tau flavor. But that amount of of muon and tau flavor that it gains is proportional to the distance. So for these downward going neutrinos, which only travel 15 kilometers, it's basically all a muon neutrino. But as it starts to travel more and more, so as the angle with respect to your detector gets larger and larger, that tau component becomes larger and larger. Until finally, when you get to the other side of the Earth, it's about 50-50. So the muon component of the neutrino and the tau component of the neutrino are split. And so this is outlining the importance of having a distance-dependent effect to explain this phenomenon. So in other words, the rate of, in your detector, the rate of a muon neutrino producing a muon that you would then observe decreases with the distance traveled of the neutrino. So this is the idea, but let's try to do a test of this. So there were two experiments built in the 90s to definitively answer this question to see if this was actually what was going on. The first one was Super Kamiokande. This expanded the Kamiokande physics program, and its goal was to do precision solar and atmospheric neutrino measurements. This is actually a joint effort between the original Kamiokande collaboration, joined by the IMB team. So IMB joined the experiment, and they helped build Super K. Then the other one was SNOW. So this is the Sudbury Neutrino Observatory. It was a low background experiment built deep underground, just like Davis's experiment, and it used a new detection technique to help answer this question. So first, I'll talk a little bit about Super K. This is what it looks like from the outside in Japan. There's a mountain here called Mount Ikeno, and the detector is placed under the mountain, so about 1 kilometer below the top of the mountain. Inside, it looks something like this. This was a photo from its construction around 1993, and it's been taking data since 1996, and it's still taking data today. So compared to Kamiokande, it was an order of magnitude increase in the volume. So 50,000 tons of water, that's about equivalent to 20 Olympic swimming pools. So it's a pretty big tank of water. And then also a big increase in the number of phototubes on the side. So Kamiokande had about 1,000. This one has 11,000. Here are some photos from the inside of the tank. So the total depth of the tank is about 40 meters. And then to actually service the PMTs on the side, you have to go around by boat to see them, to access them. Here's the detector when it was nearly filled with water, just like before, but now a much deeper pool. Also, just a personal side note, I got to go into the tank in 2018, so I got to ride around in the rowboat. It was very fun. It's also very disorienting because you can't really tell north, south, east, or west. It looks the same in every single direction. So yeah, a very cool experience. But anyway, what do you get when you scale up your detector like this? So you get these beautiful images of shrink-off rings now. So compared from before with Kamiokande, you now have much finer resolution on all the on the light that is being produced by these particles. So you can really tell that this is a sharp muon ring, and it's fundamentally different than this fuzzy electron ring. So you can tell the flavor of the particle very well. And also the extra light and the extra information lets you get a much more precise direction or energy of the particle that was interacting. So what did Super Kamiokande see compared to Kamiokande? So here's another view of the same atmospheric neutrino data in this multi-GeV channel. On the bottom, these are the events that looked like sharp rings. And what you can see is that they confirm the Kamiokande measurement. So again, over here, these are the downward going ones, and these are the upward going ones that travel on longer baselines. And what's being plotted here is, in these shaded boxes, the expectation, and then the line is showing what you would expect if there is indeed the muon component switching into a tau component. So their data really fits very well, and it's much more than a hint. It's a very significant result, because this is so far away from the expectation, and it fits so well with what you would get if you introduce this extra effect from the neutrinos. So the other experiment that's part of the story is the Sudbury Neutrino Observatory, or SNO. So this is a smaller detector than Super K, but still very impressive. So it used about 1,000 tons of heavy water, and they placed that heavy water in this acrylic shell that's shown here. And then the rest of the detector they fill up with water that acts as a shield. So it's a very low background experiment, and they also put it underground in a mine. And they do that for the same reason that Davis did, is because they wanted to shield against cosmic particles. So here's a map of the mine. This is the Creighton mine in Ontario. So the SNO detector is all the way down here at about 2,000 meters around. Compared to the CN tower, you can see it's incredibly deep. So the backgrounds in this experiment are very low. But they have to be, because the detection technique that they're going to use is different than what was used by Super K. So it is still fundamentally a Shrenkov detector, like Kamiokande and Super Kamiokande. But instead of water, it uses heavy water. And the trick here is that the extra neutron makes all the difference. So in heavy water, you have deuterium replacing the hydrogen in the H2O. So every hydrogen comes with an extra neutron. So how does that work? How does that allow you to see something new? Well, so for these reactions here, this first one where the neutrino interacts with the deuterium, it can change one of the neutrons in the deuterium to a proton, and you can then see this electron that comes out. But in order for this reaction to happen, the neutrino has to be an electron flavor. On the other hand, you can also have this process where the neutrino interacts and it just breaks up the deuterium. It splits the deuterium into a proton and a neutron. And because there's no lepton number or change in lepton number between the left and right side of this, this can be any flavor of neutrino. So now you have one detector that can see both of these different interactions. And it can also tell the difference between these types of interactions. So in one case, you're looking for an electron, in the other case, you're looking for the neutron. So in one detector, you can see both types of these things. And the expectation when you have a neutrino that is made up of different flavors is that this first reaction should be reduced because it should be reduced proportional to how much electron flavor is in the neutrino. But this process should be unaffected, just like we saw in the diagram from before. So what did SNO see? So this is a kind of complicated plot, but I'll walk through it. So the horizontal axis here, this is the boron 8 neutrino flux if you assume that it's all electron flavor. And this is the boron 8 neutrino flux if you assume it's all, or it's composed of muon and tau flavor neutrinos. Okay, so this first band here, this is the prediction of the total rate of neutrinos. So the reason it's diagonal is because every point on the horizontal axis plus every point on the vertical axis sums to the same number. So what John Bacall is predicting in the standard solar model, which is SSM here, is the total rate of neutrinos. The standard solar model doesn't know about neutrino flavor. It just says this is how many neutrinos there should be. And what was thought at the beginning is that all of them should be electron flavor. So all of them should be over here. But Davis and the SNO experiment measured about 1/3 of that. So SNO confirmed Davis's measurement by looking at their events with an electron. They confirmed that the processes that require there to be an electron neutrino, they also get about a third of those. But then if you look at the other channel that they measured, the channel that didn't require a specific neutrino flavor, what they measured was this. They measured a band that was totally consistent with what Bacall had predicted. So they confirmed that the total flux of neutrinos was correct, or it matched John's model. So here's another view of this, just now showing on one dimension. If the vertical axis here is the neutrino rate, then what they measured, another way of saying this is this process that involves the electron, that requires the electron flavor, about 1/3 of that. And then on the other process that they measured, that doesn't require a particular neutrino flavor, they measured it in perfect agreement with what Bacall had predicted. So in order to see all the neutrinos, you have to look for a flavor-independent process, is what was learned. And this provides evidence that the neutrino is not just one flavor, but it can have multiple flavors. So there were 2 Nobel Prizes that I'm going to highlight here. So the first was in 2002. Ray Davis Jr. Received the Nobel Prize along with Masatoshi Koshiba, who was one of the pioneers of the Kamiokande program in Japan. And their line here was for pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos. So a really big accomplishment here, using neutrinos from natural sources to study something about the sun, about the universe. There was also a Nobel Prize in 2015 from collaborators from the Super Kamiokande and SNO experiments that helped nail down this flavor change in neutrinos. So the tagline here is for the discovery of neutrino oscillations that show neutrinos have mass. But unfortunately, we're going to have to wait till next time to see what this means. Okay, I just want to end with a couple things about solar neutrinos today. So the solar neutrino program is still a very active area of research, and in particular, there's one experiment that has really outperformed all the other solar neutrino experiments that are out there, and it's called the Borexino experiment. You can think about Borexino as like an onion. So they take the same concept that SNO used, where you have one inner volume of material that you're looking for interactions in, and then you have an outer layer of material that helps reduce backgrounds. But Borexino has taken this to the extreme, where they add a very particular mix of chemicals in the interior that's contained within a nylon vessel. Then they have an extra layer of a buffer liquid, and then the whole thing is in a tank of water. And that means that any radioactive background is reduced as much as possible. It's basically impossible to get into the inner vessel unless you're truly a neutrino. Only neutrinos can make it into the inside. So it's ultra clean. And what Borexino reported recently, just in 2020, is this is data from the Borexino experiment. They reported an observation of the CNO cycle of solar neutrinos. And that's really cool, because this is probing how much metal is in our sun using neutrinos. So just a very unique way of making this measurement. So this is Bacall's kind of dream realized, that you could use solar neutrinos as a tool to understand the sun. So what's being shown here is the number of events that they observe in each bin of energy that they measured. And most of the things that are here are actually background. So even though they're a very low background experiment, there are still backgrounds that they can't totally eliminate. And the CNO contribution to the whole spectrum is this red line here. And what they found is that without accounting for CNO neutrinos, you can't fit the data that they observe. So they then infer that there must be CNO neutrinos present at a particular rate to explain their data. So this is a great application of solar neutrinos. Atmospheric neutrinos, this is a topic that's near and dear to my heart. So one thing that we're looking for in atmospheric neutrinos these days is whether or not the core of the Earth actually has an effect on how the flavors of the neutrinos change as they pass through it. So again, on this diagram of the Earth here, you can imagine that the Earth is not just one fixed density. There's actually a very dense iron core at the center of our Earth. And you can look for the effect of that core on the neutrino flavors. I did this experiment, or this measurement with Super K, which has a lot more data since 1998. So here's what the Super K data looks like now. There's so much data you can really split it into a lot of different types of channels. And then this is the cover page of my thesis that I made this measurement with. So to just wrap up and conclude, we use natural neutrino sources and new detectors to discover a very fundamental property of the neutrino, which is that they change flavor. But in order to better measure this effect, we'll have to design experiments that are specifically tailored to explore it. So that will be next time when we go back to reactors and neutrino beams. Thank you.